네, 안녕하세요. 네, 김해영대학교 화학공학부 조교수 조신훈이라고합니다. I see a couple of foreign correspondents, so I'll conduct this talk in English for this session. Okay, so I'll be giving a talk on sculpting the plasmonic responses in nanoparticles by directed electron beam irradiation. Surface plasmon resonance occurs when free electron carriers that are confined inside a nanoscopic space, such as nanocrystals, which are smaller than the incident wavelength of incident light. When it's smaller than the incident light, the free electron carriers can coherently oscillate within this small confined space. Now, the absorption frequency is dictated by the concentration of free electron carriers within the space. Pretty much an analogy is you can look at it as pretty much as a spring where the free electron carriers are being coherently oscillated. And due to this oscillation energy loss, very intense absorption can occur, especially in the dielectric constants of the imaginary dielectric constants, according to the Lorentz oscillator. So now, if in the case for plasmonic doped oxide nanocrystals, the free electron carriers can be significantly more reduced as compared to typical metals such as gold and silver. So we can have great transparency in the visible, but a very highly intense absorption in the infrared, pretty much for example, in sunlight. So what can occur is we have a whole wide variety of library of doped metal oxide nanocrystals that can be pretty much used in blocking the infrared energy light from light sources such as the sun. So how can we procreate these free electron carriers? We can borrow a strategy from the semiconductor industry where we use N-type dopants within a nanocrystal lattice. For example, in the case for indium oxide, we can dope fluorine or tin within the lattice of the nanocrystal and procreate such free electron carriers. So for the synthesis aspect of it, we can synthesize nanocrystal cubes, fluorine, co-doped tin, indium oxide. We can, as you can see, it's quite transparent if you have a dilute ink that is dispersed in hexane. But if you look at it in the infrared camera, you can see very intense absorption occurring. Now, in the case for faceted nanoparticles, this is a PIR spectrum. We can see a breakdown of multimodal peaks that occur due to the corner, edge, and face on the morphological discontinuities. And in the morphological discontinuities, you can see that in the corner of such nanocrystals, very intense near-field enhancement occurs within such discontinuities. Now, pretty much before transferring into the academia, I was pretty much working as a staff engineer at Samsung Semiconductor R&D, and state-of-the-art top-down methods such as EUV lithography is quite catching up into the nanoscopic space. For example, in EUV lithography, the industry is currently targeting sub-3 nanometer scale multi-pattern scheme with multi-million-dollar equipment. So I've been inspired by merging top-down methodology with bottom-up assembly, such as self-assembled nanocrystals. So in this study, which with our Oak Ridge Labs collaborator, published just freshly last year, we merged E-beam single particle drilling methods in self-assembly of nanoparticles. This is pretty much like a TEM image of a time series from 0 to 2 minutes in a single spot drilling of a single nanocrystal. So we can see that the crystallinity is quite well preserved. Meanwhile, having specific design-targeted drilled holes in individual nanoparticles within pretty much the scale of 5 to 3 nanometers even. Now this is a Gaussian filter 3D net reconstruction profile. So we can observe that indeed a deepening of the hole of such E-beam lithography method can be observed. The nanocrystal individual drilling can be done by STEM, by using a STEM electron beam operation. Accelerating voltage is quite high at 60 kilovolts, and the probe current is added even higher at 500 picoamperes. So the current density can be pretty much in the scale of 10 to the 6th amps per centimeter squared. So what does the near field look like? With specialized STEM EOS imaging technique provided by Oak Ridge National Labs, within the drilled nanocrystal, we can see a very highly intense, pretty much in the third line over here, you can actually see a very highly intense localized plasmonic near field enhancement occurring in such holes. So pretty much it's a way of using a top-down approach, it opens a way of designing near field enhancement in a designated location as we want. So we pretty much expanded upon this method using, we can even expand upon selective single particle modifications such as various checkerboard spaces, or even ring resonators, attempt to use ring resonators. And it'll be an interesting pathway to open a path for quantum information, write and read functionality through infrared plasmonics in such self-assembled particles. We attempted to try to track down some of the chemical changes from such electron beam irradiation. We suggest, although this isn't a complete study, but which we will also want to further probe, but it does suggest a two-part mechanism where during the first stage, the destabilizing removal of oxygen occurs, especially in the region of indium oxide at 485 electron volts, first initially disappearing within the time period of 0 to 3 minutes, excuse me, and then at the second stage where indium is removed after the oxygen destabilization. What we can also see in the elemental mapping is we can actually see the substrate. We can actually see the indium oxide nanocrystals completely being drilled completely through, all the way through the silicon nitride grid, which we've been using in order to support the substrate on the STEM EOS. So we can indeed confirm that the holes are completely being disintegrated into all the way through. Now, what are some of the pathways that we can expand upon? That was the previous studies in just our recent publication with our collaborators in drilling holes. What are some of the future directions that we can do for further analysis? Some things that we were trying to do is by using VBA, or variational autoencoder machine learning analysis, in order to really track down some of these very complex plasmonic modes that are quite hard to do even with single particle analysis, although it is quite approachable to do with FEM simulation methods. But in more complex interparticle landscapes, such modeling methods are quite difficult to do. So an outline of that would be using autovariational autoencoders in order to track down, extract EOS spectra data in individual pixels, and then mapping them out in latent space and auto-classifying them, and using STEM EOS reference. You can use auto-classification in order to automatically track down such features such as voids, gaps, or edges of such complex nanocrystal structures in thin film nanocrystal structures. Since the time is allocated, I'll quickly run down some of the source code that was provided by our Oak Ridge National Lab collaborator, Maxim Zyetinov. The first stage would be just initially extracting the hyperspectral maps that are pulled out from STEM EOS. So from this information, we can have spatial features, but also within the individual regions of interest, we can pull out the electron energy loss near field data. We undergo variational autoencoder training processes with multiple iterations. What we can do is then we can start reconstructing, well, not reconstructing, but rather auto-generating various spectral features, which is pretty much dictated by two dimensions. One would be the intensity of the electron energy loss spectroscopy, and the second would be the peak position of such plasmonic modes. Then it is mapped out through, in latent space, as mentioned, Z1, Z2, that will be the intensity and the location of the peak. And with clustering, nearest neighbor clustering methods, we can, with unsupervised learning, the code itself would be able to classify specific features. In this case, we have a bandwidth tuning of around 0.50, but we can always tune it up. We have different, we can add even up to 6 features, tune it down, then it becomes clustering 2, etc., etc. And through that, we can generate, through training method, we can map out the representative energy loss spectra, the near field spectra, and by overlaying it with the spatial feature map, then we can, remarkably without human intervention, we can classify such features such as voids and the edges of nanocrystals, along with the inner particle gaps, along with the bulk of the nanocrystal. So some of the future ahead, perhaps it can be used for forward prediction of complex near field yields map with individual training data that is collected from such yields map. So there will be some interesting features ahead in this process. We'd like to make some acknowledgments. Last semester, after joining Keio University as a faculty member, we had our first fab out. We have finished setting up our lab. We had our first Plasmonic nanocrystal synthesis out at just at this time. Pretty much the name of the lab, the shrink line would be called NL1. It's the first generation synthesis bay, specific for doped plasmonic oxide nanocrystal synthesis. And I'd like to really acknowledge the early undergraduate student researchers that are joining the shrink group, able to successfully set up the shrink line and also independently make and fab out such first nanocrystals. Also, our collaborator acknowledgements for both of the studies that have been outlined. Oak Ridge National Labs, Kevin and Jordan, for providing STEM yields experimental data, and also the Oak Ridge National Lab machine learning analysis team, Maxim, Sergi, and Rama, for developing and continuously communicating with electron microscopy scientists, synthesis, and developing further fine-tuning such source code. So thank you. My group side will be over. If you have any interest in our publication, you can check out our link. And yeah, thank you for attending this talk.
이준 교수님 발표 잘 들었습니다. 질문 있으시면 한글로 편하게 말씀해 주시면 되겠습니다.
Yeah, go ahead.
Thank you for your talk. Is it possible to make the semiconductor so degenerate that it actually starts absorbing invisible light, like gold, silver nanoparticles, or would the semiconductor just...
That's an interesting question. Yeah, I mean, this is a task that I'm trying to continuously overcome. The free electron carriers, definitely it is lower than the metal. I'm not sure if we are able to turn it completely into the visible. Now there is one other oxide class where, for example, tungsten oxide does have higher free electron carriers due to polaronic effects, but also cadmium oxide, fluorine doped or fluorine doped cadmium oxide does approach near to the near infrared. It tunes slightly more higher than ITO. But yes, I pretty much during my PhD I've been trying to raise it all the way closer to the visible. So this is something of a task which I'll still continue to do while working in this group. Yeah, that's a good question there. Yeah, yeah, it's hard to do. Yeah.
One more.
Yeah, go ahead.
With the electron beam lithography, you start with the cubes and then you make a hole in it. But once you shoot the electron beam on it, the atoms that are discarded,
yes,
they're just lost. Or are they redeposited?
Yes.
The edges?
So pretty much it does break the vacuum a little bit. So this is where the electron microscopist doesn't really like it. Now, in the case over here, it does seem to deposit. If you look at the inner particle gap, most of them it is lost into the vacuum trap. Although if you try to annihilate the particles altogether, you can see a little bit of damage in between the particles. But the point of this supplementary data is that with the electron beam lithography, it does not break the crystallinity around the point of interest. Now, we do see a bit of deposition. So yes, we do have to break the trap, so we'll have to, in a manufacturing way, there has to be a way to purge these metals and oxygens out.
다른 질문 있으신 분? 제가 하나 질문을 하면요.
네.
아까 질문과 조금 연계가 됐는데 이렇게 이제 파티클을 나노 파티클에 이레디에이션을 하면 디펙트처럼 작용하지 않을까 싶은데 그랬을 때 그것이 서비스 플라즈몬에 미치는 영향은 어떻게 될까?
이제 디펙으로 이제 하는데 저희가 이건 구체적으로 뭐 들어가지 않았지만 체커보드 모양으로 만약에 있다면은 이게 그 니어필드 자체가 그 보이드 안에 있기 때문에 근접장 자체가 뭐 렌즈처럼 이제 여기 그 비어 있는 공간, 이 디펙트 피처 안에 더 집중되고 있는 겁니다. 예를 들어 저기 가장 이제 오른쪽, 제가 보기에 오른쪽에 있는 여기 본다면은 좀 근접장 신호 세기가 이제 좀 상당히 한 5배, 한 5폴드 정도 이렇게 좀 또 강조가 되는 그런 게 있습니다. 링 레저네이터라고 한다면은 저희가 도넛 모양으로 하게 되는데 우리가 좀 뭐 아직 더 구체적으로 봐야 되겠지만 그 서페스 플라즈몬 형태로 마치 서페스 플라즈몬이 되는 것처럼 로컬라이즈드가 아닌 뭐 디로컬라이즈 서페스 플라즈몬 링 스트럭처를 한번 좀 만들어서 레저네이터를 이제 만들려고 하는 그런 좀 시도를 한번 해봤습니다. 광학적으로 디펙을 말씀드린다면 그렇게 답변을 하겠습니다.
근데 그 디펙트에서 더 인텐스 된다고 말씀을
예.
하신 것 같은데 그 원리가 어떻게?
그 원리라면은 시뮬레이션 모사 모델이지만은 이게 모폴로지컬 디스컨티뉴이티, 그러니까 이제 계면상으로 이제 좀 꺾이는 그런 지점이 생기면은 이제 그 근접장, 그 나노 안테나 효과를 위해서 이제 근접장이 이제 발생하고 있습니다. 근데 만약에 보이드가 생긴다면은 하나의 파티클이 아니라 그 주변, 이 그 빈 공간에 있는 주변에 있는 나노 입자들이 컬렉티브하게 그 근접장 모드를 이제 합쳐져가지고 그 비어 있는 빈 공간에서는 그 니어필드가 증폭되는 그런 효과를 지금 보이고 있습니다.
질문 더 있으신 분? 하나 더 제가
네, 재밌습니다. 네.
이 UV 리소를 보여주셨고
예.
이빔으로 실제로 이레디에이션 하셨는데 이빔을 쓰신 이유는 어떤?
그 사실상 이게 좀 우연한 나름 발견입니다. 저희가 이제 원래는 그 일렉트론 마이크로스코피를 하면서 빔 데미지를 최소화를 해야 되는 게 이제 그게 정석입니다. 하지만은 일단 우리가 스템 일시를 하면서 우리가 목적은 그 근접장에 있는 효과를 계속 관측하는데 재밌게도 같이 이제 좀 콜라보레이션 하다 보니까 빔 데미지를 먹는데 얘를 더 세게 빔을 데미지를 먹으면은 뭐 리드 라이트처럼 이제 그런 정보도 저장할 수도 있고 아니면 근접장을 인핸스먼트 우리가 디자인하는 대로 할 수 있지 않을까라고 했습니다. 좀 약간 우연한 발견이 좀 된다고 보시면 되겠습니다.
감사합니다. 네, 더 질문 없으시면 조진 박사님께 박수 드리고 다음 연사분 모시도록